So I would like to start this second class about stochastic processes with the exit point distribution. So and conditional process. So this will be part number 2. Part number 1 was the Ito calculus. So today I would like to discuss the following question. Suppose we have a domain and the general formula for the stochastic dynamics perturbed by noise is going to be x dot equal b of x plus, let's say, sigma w dot, where this is our classical Brownian motion and this is a drift term. Now suppose we start at position x inside. So we would like to estimate what are the distribution of exit point located on the boundary of the domain omega, on d omega. So you start from x, you look where the particle exit, you start again, and so you have a distribution of exit point which can be characterized by the following probability. So we are interested in the probability that x of tau, which is the time it exit condition that the particle started at position x, exit at position, let's say, y plus ds of y, condition that x0 at time 0 was equal to x. So this can be written as, this is the density function starting from x to y, dsy. So this is a measure on the omega. So how to calculate, so what we are going to be interested in here is how to calculate, how to compute this density, the density P. So for this, we are going to use Ito's formula. So let me remind you what we have discussed in chapter 1, in part 1. We said that for any function f, we can estimate d of f for the process x of t, and this could be written as an operator L tilde of f of x of t, and this is dt, plus a term that depends on the noise, which is the sum of sigma ik. So this is the matrix here associated to sigma ik, and this is df dxk d omega I of t. So this is at position x of t, and now we have to solve for I and k. All right, and so this is true, of course, for all function f sufficiently differentiable, and so true for all f, regular f. And so we are going to choose a clever function f such that we'll be able to find a solution of a partial differential equation for the density P. So for this, let's choose the following equation. Let's suppose we impose that L star of P, of U, let's call it F, equal 0. This is on any point in omega. So this means that L star of f of x equals 0, where I shall remind you what is L star of L. This is the sum of sigma transpose divided by 2ij ddf dxi dxj, sum over I and j, plus b I ddf dxi sum over I from 1 to n, where omega is of dimension n. And this is inside the domain, and now we are going to impose that on the boundary f of x equals to a function phi of x, and we will see what function phi we shall choose. So for x belonging to the boundary d omega. So in that case, let's rewrite the Ito equation, and let's take the expectation of the integration of the Ito, which is f x of t minus f at position x, which is x0. This is equal to the integration. We have to integrate from 0 to t of the part L star of f of x ds plus the stochastic part, which is integration from 0 to t. And so this is, let me write it, the stochastic part. Okay, I will write it again. This is the sum of ddf dxi of sigma ij d omega j. Right, so now let's take the expectation of everything. So of this, which is equal to expectation of all of this. So the first term can be written, this term here, when we take the time t equals tau of x for which the process is on the boundary. So this is precisely the expectation of f at a point on the boundary. So this is clearly expectation of phi of x, and this term can be written using the probability density function. That is, suppose we condition that this point is exactly equals to x. So this is the integral of f of y multiplied by the density to switch, to make a transition starting from x to point y, so p, x, and y, and then we have to integrate over the boundary ds of y, d omega. So the second term here is just a deterministic term. This is f of x. So we have this. So let's write it minus f of x. By definition, this term is equal to 0 because of, let me emphasize this in red, because this is exactly chosen this way. So this is exactly 0. And this, as we have seen before, because d omega, this is a non-anticipating function, and the expectation of d omega is exactly 0, then this term is identically 0. So finally, what have we proved? That this has to be equal to 0. All right, so it means that the function f here is equal to this term. Now, what is the function phi that we shall choose in order for f to be exactly this density? So either we can decide to find a sequence of function that converges toward the delta Dirac at a point y. So let me just, so we have here the domain. We start at point x, and we want to escape at point y. So we can choose a delta Dirac precisely located around this point. So either we choose a sequence that converge to a delta Dirac at that point, or we just take the f equal delta Dirac y. So in that case, this integral is nothing but the probability of making a transition from x to y, and this is equal to f of x. So we have seen here that if we choose for phi the delta Dirac, P is a solution of a partial differential equation that I'm not going to summarize in the next slides. So we have L, the operator L omega of P equal 0 on any point inside the domain. We choose Px equal the delta Dirac at y. And in that case, the solution of this partial differential equation is precisely the probability, this is the probability density function for a process to start at x and to exit at y. This is exactly this probability. So again, we have to solve, if we want to compute P, this requires to solve a partial differential equation, a PDE, which is here, it is of elliptic type. And when sigma is not degenerated, which means that we have the determinant of sigma at any point which is not 0, sigma ij, at any point x, this is not 0, then we have a non-degenerated elliptic equation, and we know that there is existence and there is a unique solution. This is from classical theory of PDEs. So now what I would like to do is to give an example of how to calculate this probability P. And this is called so we have now finished with the derivation. So I would like now to go to the example of the Poisson kernel. So what is the Poisson kernel? Let's do the following example. Let's take a disk in dimension 2. And we are interested in the Brownian motion, x dot equals, let's say, square root of 2d w dot. And suppose we start from position x. What is the distribution of exit point py condition on x? So if x is the center 0, we can imagine that the probability, which can be parameterized by the angle theta here, if we parameterize this with the angle theta, if we start precisely at 0, then every point here by symmetry is going to be achieved with the same probability. So then the density is going to be the theta divided by 2 pi. But what happened when we start not at 0 but at position x? How shall we solve this problem? So for this, first of all, what is now the equations? The distribution of exit point equation. Distribution of exit point equation. We are exactly going to apply the previous derivation, the previous calculation. So since we have just pure Brownian motion, the drift is 0, and so sigma now is the identity matrix. This is 2 square root of 2d multiplied by the identity matrix. Thus L star of P is reduced to 2d. This is sigma sigma transpose divided by 2. And since we have identity, the second order term is just the Laplacian. So we can now remove the 2. And so the equation is this has to be equal to 0. So actually the d is unimportant. So the equation is Laplacian p equals 0. And on the boundary, we have to impose a delta Dirac, or another way is to impose a function phi. And we have to solve this on the disk of 0, 1, and this is on the surface of the disk. Alright, so if we know how to solve this equation, then we'll be able to exactly answer the question we ask, which is find this the analytical solution for this probability density function. So, alright, so now how to find, first of all, the solution of Laplace equation in a disk in dimension 2. So this is not that difficult. Just to remind you the basic approach, Laplacian p can be written in a polar coordinate as dp dr square plus 1 over r ddp dr plus 1 over r square ddp d theta square equals 0. So how to solve this equation in general? We have to use separation of variable, that is p, r, and theta equals a function phi of r multiplied by a function, let's call it psi of theta. And now what we need is to find a solution for phi and a solution for psi. And so this can be done just plugging into the equation, and what we get is phi second. So let's plug this into this equation and divide by phi and psi. So we got phi second, so 1 over phi plus 1 over r phi prime plus 1 over r squared, and this is now we are left with psi and psi second divided by psi. This has to be equal to 0. So if we multiply everything by r squared, so we have here, so I can multiply this by r squared and this by r squared, so this goes away, and this depends only on psi, on theta, and this depends only on r. Thus, each term separately, they have to be constant. So let's say that this is equal to minus lambda squared. So we have psi second plus lambda square psi equals 0. So this is for the variable theta. And for the variable r, we have phi second plus 1 over r phi prime. So this is going to be minus lambda square phi, and I have to divide here by r squared, equals 0. And this is for the variable r. Alright, so now what needs to be done here is that since the solution has to be periodic in theta, the possibility is, of course, psi has to be the sum of cosine. So this is a cosine lambda theta plus b sine of lambda theta. Right, and so now since it has to be periodic, we need necessarily to have that lambda, it has to be 2 pi periodic. So the only possibility is that lambda has to be equal to, has to be in z, right? So that lambda can be equals to, of course, 0, 1, 0, 1, 2, and so on, or minus 1, plus or minus. and plus or minus 2. All right, now we have to find the solution for phi. So again, this is this can be expanded. It's a space of dimension 2. And so I propose that you try the following solution. Phi of the type is of the type r to the power, let's say, alpha. And so let's plug this into here, and you see what's the solution. So the solution is, so if we derive once phi prime, this is going to be alpha or alpha minus 1. And if we derive twice, make a second derivative, this is alpha minus 1 multiply by r to the power alpha minus 2. Right, so now if we plug back everything into this equation, what do we get? The second derivative is alpha minus 1, r alpha minus 1, now alpha minus 2, plus alpha r to the power alpha minus 2, minus lambda, so lambda is the integer number, so let's write it n squared, divided by r squared, so this is alpha minus 2 equals 0. So finally, this means that if we remove r, this has to be equal to alpha squared minus alpha plus alpha minus n squared equals 0. So this goes away. And finally, alpha has to be equal either to plus or minus n. And so now we are ready to write the solution for this equation. So the solution, so let's continue. So we need to have to expand the solution p r of theta. This can be expanded into the basis of a solution, which is actually here because we don't want to have any singularity at 0, and we have potentially L to the minus n, but this has a singularity at 0. So we have to remove them. So finally, the only possibility is r to the power n, I n theta, so this is a n, plus bn, and we have r to the, let's call it again positive n, and now we can have here minus n theta, and p has to be real. In addition, this has to be a real function. All right, so I think we can now write the general of the general form. This is sum of Cn exponential In theta r to the power absolute value of n. All right, so this is p r of theta inside the domain. Now, in addition, we have imposed that pr for capital R equals 1 at the boundary here. This is r equals 1. Then this has to be equal to a function phi of theta, which we can expand in a Fourier series, and this can be written as Cn, let's call it dn exponential of In theta. And we know that the dn coefficient are the Fourier transform, which is 1 over 2 pi integral from minus pi to pi of phi theta exponential minus In theta d theta. And so now we can just plug this back into this equation. So obviously, because we have a unique decomposition, dn has to be equal to Cn, and p r of theta is simply given by 1 over 2 pi, the sum of Cn, which I can now change with the integration term, minus pi to pi, of the sum of In theta r to the power n, and let me change this. I'll call it this new variable. I call, instead of theta, I call it u. So this is phi of u exponential minus n u du. All right, and so this is precisely what we have to compute. So I'm going to leave this as an exercise to calculate this sum, because this can be written as just, you know, a classical geometrical sum. This is integration from minus pi to pi of what? Of 1 minus r squared divided by 1 minus r exponential I theta minus u squared, and this is phi of u du. Right, and so by definition, now if we are interested, if we come back to the definition of what is P, this is the probability to starting at position r and theta. This is the probability to escape somewhere at a radius 1 and at a location u. And so this is exactly, once we take the phi, which is delta Dirac, let's set position delta Dirac at u, this is 1 over 2 pi 1 minus r squared divided by 1 minus r exponential I theta minus u squared. Right? So this is exactly the interpretation of what is this kernel. This is the probability starting from let's say r and theta to escape anywhere at position 1 and u. And you see, this is of course far from being what we found when we start at the center. All right, so I'm going to close this this part here of the class, and this is an illustration of how we calculate, how we can compute the the distribution of exit time. In practice, of course, in a general for a general domain and general dynamical system, this calculation is usually not possible, and asymptotical analysis is necessary.